Does that look good for everyone?
Is it really on YouTube?
Yeah, I think so.
Okay.
I'll join the meeting on my iPad so I can see audience questions, and then they can tell me in the chat if they can't hear.
Maybe 2 more minutes. Okay. I know that people won't be wrong. That's fine. Yeah, I didn't speak up to
Okay, ladies and gentlemen, welcome to the 5th in our colloquium, in our philosophy of physics colloquium. Today is our great pleasure to have Professor Fedele Lizzi here. Before Professor Huggett is going to introduce our speaker, this event is co-hosted with the University of Chicago. It's my great pleasure to announce our visitor, Abigail Holmes from the University of Notre Dame in Indiana. She's currently visiting us and a PhD student of John Howard's with special interest in the philosophy of astrophysics and cosmology and working on the Hubble tension. So now to you, Nick.
Yes, okay, so it's funny. So in fact, I guess it's co-hosted with the Beyond Spacetime project, I should say. Although we managed to, Chris Butrick and I managed to mess up rather spectacularly, and both schedule meetings at the same time. So there's sort of another half of this talk going on in Lausanne by Sam Barron. So apologies for that.
Been an entangled sense.
Well, I think they're recording it, so we can find out later. Anyway, I'm very happy that James, who's at a conference in Italy, ironically enough, at the moment, or is headed that way, and I were able to arrange for Fedele to come speak today. So I've been talking with and working with Fedele for several years. With Tushar, we wrote a paper about sort of simplest form of non-commutative geometry, deformation of regular geometry. The talk today is going to be extending this from sort of just a space context to a space-time context. It's something I've been very interested to learn more about and hear about today. It's been very pleasant to, Fedele has been a great person to work with, and I've learned tremendous amount. And it's also interesting, well, to me at any rate, that we kind of overlapped. We actually both arrived in Oxford at the same time. First times, I guess, back in 1985, when I arrived as an undergraduate. Fedele arrived as a postgraduate, fresh from Syracuse, I think.
At the Rutherford Lab.
To the Rutherford Lab, but I don't know. Maybe we can cross paths at that time. That
I was open in the university here, but I was never paid by this university. It was on Her Majesty service.
Right. Okay.
It was a civil servant.
So, but for a long time, Fedele's been at the University of Naples. Yeah, we're very happy to have you. Please tell us about
Okay.
Kapp-Minkoski.
So where should I stay in order to be seen? Not that it's a okay.
Basically, the board is your.
Okay, here, basically, okay. So the title is Quantum Observers for Quantum Space-Time, but what I will most talk at the beginning, at least, is non-commutative geometry and the need for a non-commutative geometry. I will get to Kapp-Minkoski slightly later, and it's difficult to give a talk to audiences, and it's more difficult to give a talk to non-physicists for me, but I have had some experience in dealing with philosophers. So especially the Anglo-Saxon, although Anglo-Saxon school, although no, because in Italy it's more difficult, because in Italy, especially in Naples, the Benedetto Croce school, so it's difficult to be technical. So I assume that you are familiar with notions like wave function and something. Some of the slides have a different background, more reddish. I hope it will come, because as a physicist, I'm deontologically forced to show you some formulae. I cannot go from A to, it's just against my, without showing how I get there. So some of the slides, if you are not that conversant with the Mellin transform, etc., you can just integrate them out in physics parlance. But in general, I'll try to. And so let me start with the usual introduction, which would be common to anything I say. And okay, fundamental physics, the problem is the construction of quantum gravity. I will not construct it here. Gravity is the theory of curved space-time, and the difference with other theories that the dynamical variable is space-time itself. So one can try to do a quantum field theory. Quantum mechanics should be quantum field theory, or we'll see later on that we can probably be happy with something less. But and this creates a problem. If one goes just straight saying that G mu nu is the graviton, so I do this field theory, this one doesn't work. It's not renormalizable, and so I have to do something else. So the idea of quantizing a spin-2 field doesn't work, and nothing works, basically. So we don't have a theory of quantum gravity. But let me say, the point of view which I will take is that I'll take the point of view on non-commutative geometry. So if I want to quantize space-time, I need to have a quantum space-time. And I will concentrate on the description of this quantum space-time, so on kinematics. So how I can describe a quantum space-time. And one way of describing something quantum is to have coordinates which don't commute. This is not the only way, but it's something which did us some good for quantum mechanics. And so it's not the only way to do non-commutative geometry, but there are many ways to interpret non-commutative geometry, and I call them flavors of non-commutative geometry. I will concentrate on Kapp-Minkoski, but there are more mathematical point of view, and the original one was based on work by Alain Kohn, is based on spectral property of algebras and operators. Here I will be more down to earth. So for me, non-commutative geometry is non-commutative coordinates. It's like saying that quantum mechanics is x and p which don't commute. And this is certainly true, but you can do quantum mechanics in a purely algebraic way, just taking theory of bounded operators and something. So I'll take the simpler point of view. I can go from one to the other on demand. Okay, so the question, since I work on non-commutative geometry, the question that I've been asked usually by experimental physicists is, what is non-commutative geometry? What does it, what's good for it? And of course, I had to answer that because I need to get money for this. And there is one non-commutative geometry that we all know, and is quantum mechanics. The phase space of quantum mechanics becomes non-commutative when I do quantization. So classical mechanics is a theory of phase space, the phase of position and velocities. Momentum is not exactly velocities, but if I don't have, so if I know the position and the velocity and eventually all the fields around it, then I can follow the path of the particle. And now there is, I know that I must do something to the classical phase space. So the classical phase space cannot be made of usual points. And this is the Heisenberg microscope. Probably you know it. So the Heisenberg microscope uses two quantities, very important. One is the speed of light, which is a dimension-full quantity, which is a cutoff on velocity. And the other is the quantum of action, which is h bar, which is, well, one is very large, or 1 over c is very small, and the other one is very small. And then it was clear by the photoelectric effect, or at the beginning of last century, that light is made of photon, and the energy of this photon is inversely proportional to the frequency. And this is the Heisenberg microscope. So if I want to know where a particle is and what the momentum is, but let's start first asking where the particle is, I should send some radiation on it. Radiation electromagnetic, it's more convenient than sending neutrinos on it. So I send radiation electromagnetic, and then if there is something there, I will give a kick to this particle, and then if I have a large microscope, then I will see the scattered particle, and I know more or less where it is. The more or less is because, of course, the lens is bigger, and I have to reconstruct where the object is coming from. The light will have a wavelength, so I cannot make this wavelength arbitrarily small. Well, I can make the wavelength arbitrarily small, but if the wavelength is very small, the light will have a large energy. And so I interact with the particle, but in the process of interaction, this very energetic photon give a lot of energy to the particle. And therefore, I know that the particle is there, but I cannot know what is the momentum afterward, because I have an uncertainty here, because the momentum should be such that I can capture this. This is the lens of a microscope. So you put the numbers together, the aberrations of the lens and something, and you get to something close to Heisenberg's principle. So Heisenberg, this was called Heisenberg microscope because it was something that Heisenberg himself thought of to explain. So if I want to know with high precision where the particle is, I have to renounce of knowing what is the momentum, because immediately after the interaction, the particle will have a momentum which is unknown, which will be in some range which is unknown. So I will not affirm that quantum mechanics is well understood, but we certainly have something which works. So we got quantum mechanics, quantum field theory, etc., and we have experiments with several 10, 12 digits, and so for a physicist. So I use two fundamental constants, and now I want to go one step forward. So I will not care of the momentum. I will only care of the position. Now, in ordinary quantum mechanics, there is no limit of the precision of position. Delta x can be as small as you want. Delta p will be large, but delta x can be as small as you want. So I can pinpoint the position, and I don't care about momentum. Now, I put then gravity in the game. Putting gravity in the game means that I put another constant in the game. So this is a phenomenon that was noticed by some physicists called Bronstein in 1938. Shortly after, he was caught in one of the Stalin processes, so he was basically shot shortly afterwards. I don't think because he did that, but it was somehow rediscovered and presented in a more terse way by Doppler, Fredenhagen, and Roberts in 1994. I will put another caricature of this because, like the Heisenberg microscope, and what is the same is this. So I'm not interested in momentum, and I just concentrate a lot of energy. I have a photon, a very energetic photon, and I measure the position. So if I put together the three constants, so Newton's constants as well, capital G, I have a length, which is Planck length. It's a very small length. So if I want to measure the position, I can go closer and closer to this length. But now I have a problem. If I concentrate too much energy into a very small volume, then I develop a black hole. It will be a micro black hole, nothing to do with the black hole at the center of the galaxy, etc. But the Schwarzschild radius, technically, that is the same, it's a black hole. So I concentrate a lot. I want to measure a short distance, but I create a black hole. The black hole will have an horizon. The horizon will be at this length, just putting together in the equation. And therefore, I cannot go beyond the horizon of the black hole. The black hole is something there, and I cannot probe anything inside there. Therefore, I have a limit on of what I can measure. So it's something similar. Now, of course, the Heisenberg microscope is not really quantum mechanics. Nobody will do quantum mechanics the way I was doing the Heisenberg microscope. So what do? We have a formal theory in which I have operators on an Hilbert space, wave functions and everything, and then I have quantum mechanics. And again, I said, not that we understood it, but we can work with it. For gravity, we don't have quantum gravity. So we are one step, we are at the level of Bohr and Rutherford, or I don't know. Luckily for them, in about 10 years, they solved everything. We are slower, or the problem is more complicated. And so one first thing that one thinks, it works once, let's do it again, is to replicate what has been done for quantum mechanics. So I just take the commutator between the coordinates of space-time, and I put them equal to a constant. So this is called Doppler, Fredenhagen, Roberts. There is a T missing here. It's also called Moyal, Grönwald, Moyal. Is the most common kind of non-commutative geometry which appears, is that I have x mu, x nu. Now mu and nu are coordinates in space-time. So I put time in it. Non-commuting time is a complicated thing. We'll discuss this later on. So this is a space-time replica of quantum space-time, the canonical commutation relation, and h bar is substituted by theta, which is a set of numbers which I imagine to be of the order of Planck length. And the great advantage is that everything I did for quantum mechanics, I can repeat. So I have a huge body of knowledge. And this was touched upon by a famous article of Seiberg and Witten in, I think in 1999. And so it becomes very, very common because anything that Witten knows as. So there was this famous article, and so lots of people worked on this kind of very simple non-commutativity. And let me recall for you very quantum mechanics. So I will do this as a case study, but just to set something that you probably, hopefully, have seen before. At least I have been teaching this in an undergraduate course for many years. So I take a space which is 2n-dimensional, the Q and P's, and quantization, I introduce a non-trivial commutation relation, which is this one. And in a few steps, I can get to Heisenberg uncertainty. This is delta P, delta Q. There is a delta Ij missing here. So in each direction, delta P, delta Q must be larger than this quantity. And in order to represent this, I can represent this as wave functions. So I connect Heisenberg picture with the Schrödinger picture. And I have this Q is a multiplication operator. P is a derivative. And this is the view in which I have a probability wave. And this is the square, modulus square of this is the probability to find the particle somewhere. And the result of a measure is the spectrum of these two operators. This is von Neumann idea. And if I localize things in position, I will have a delta function. And this is dual to localize them in momentum, which is a plane wave, which is totally delocalized. In between, there will be some coherent states, these sort of things. So implicitly it means that I am describing the wave function as a function of space. But then I could do the same thing as a function of momentum and not be concentrating on the probability of finding the particle somewhere, but finding it with a certain velocity. Again, let's not put magnetic fields in it. And technically means that I have chosen a complete set of observables, and the two are dual. And I can describe functions either as in space, configuration space, or in momentum space. And I have choices for complete sets, number operators, angular momentum, etc. And now comes, we were discussing this today morning. I use the word observer as nearly as synonymous with reference frame. So I have somebody that observes, and he will have a reference frame. Now, observer reference frames are not exactly the same thing, and I was discussing with Nick about the differences, but pretty much they are, that is, should I say philosophical, the same. So there are ways in which a physical phenomenon is translated into numbers. Okay, so if I have a different observer, which is translated, rotated, boosted with respect to the other one, it will have a different set of observables, different set of wave functions, everything. Just think of translations. And in order to do this, technically, I need a tensor product, but I know how to go from one to the other. I have some precise rules. I know how to rotate functions. I know how to, everything. As I do it with angular momentum, etc. So if I have different, so I'm making an experiment with my set of coordinates, and I come with some numbers, and Tushar makes an experiment, and there is a partition between us, and then he gets different numbers. When we remove the partition, say, oh, of course you have rotated, so give me the three angles, and I will and we'll agree on everything. So I work with Tushar and Nick, and I started talking about the fact that in physics, I cannot really ever localize things. I can localize things with some probability. So I can model this with a Gaussian state. And of course, also the measure will be another Gaussian state, for example, and I can make them arbitrarily small, the two of them, to the point that the overlap between the two is so small that either the particle is here or is not when I measure. And then when it's there, I read 0 until the two measuring device and state are in the same place, and then I read nearly 1, not really, because one will be probably a bit more these things. And so this is if I do this in quantum mechanics, I cannot do this in quantum mechanics. If I have a state which is localized somewhere, I can make it sharply localized in position space, but also the measuring device will be another localization. But now I have to put them together in a quantum mechanical way. So technically, I have to use a non-commutative product. The Moyal product is one way of using it. And if the states are too localized, then I don't get a good probability. In fact, there is an example in our paper. If you are trying to see a density matrix of a state which is classically localized, then you do the Weil map and you make an operator out of this. If the state is, the classical state is big enough, you have no problems. You will find a density matrix which is normal. If it's too sharply localized, your density matrix starts developing negative eigenvalues or Wigner function, if you're familiar with these things. So if you're trying to localize too much, any attempt of using probabilities in the usual sense, they fail. And in this paper, we show that classically this is okay. It's not okay. So classically, say quantum mechanically is not. However, I can try to localize, and that's what I said. As long as they're not too localized. So in quantum mechanics, points in phase space are not operationally definable because of operational density. So talking in quantum mechanics of a point in phase space is not something which makes sense. There are no points in phase space. So for me, it's a foreign language, but I say that the points are nevertheless part of the necessary ontology, because all the discussion I did was starting from phase space, which is made of points. So I'm denying the points, but I started with the points. Then I had to substitute them. And so to some extent, I need points, but I need to go beyond them. So, so this is something which puzzles me to some extent. And I'm doing quantum mechanics, which, however, is different between position and momenta, but I need to start from phase space. I cannot do it. This might have to do with personal limitation. Probably a quantum baby born quantum will not need it, but in order to do physics, there is no quantum mechanics course which starts with operators. This is a quote by them which speak natively, and you can read it. But this is what to show you that already in the simple case, when I try to take quantum mechanics and I put it into considerations of points in phase space, and I cannot have localization in phase space. If I do now non-commutative geometry of the kind that I was doing before, it means that you don't have points of space-time. Now, this is a fairly big thing, in the sense that at least we like to know where we are, and that there is not a where we are. The concept is not operationally useful. But let me now criticize this form of non-commutative geometry, and this cannot be really a representation of the universe, because I break Lorentz invariance. If I take x, the 3 variables plus time, they don't commute with this x1, x2 is some number, x1, x3 is another number. In order to do that, I have implicitly chosen 2 directions. This is technical, but I've broken rotational symmetry. Technically, I have an antisymmetric tensor, but you see that this is not invariant for rotations. And okay, there can be a fundamental directions in the universe, but actually now in cosmology, data on the cosmic microwave background are nearly killed this idea if this theta is of the order of the Planck length, because of the isotropy of the cosmic microwave background. So there should be, and in any case, if I quantize gravity, I should have symmetries. The general relativity is a generalization of special relativity. So at least the Lorentz group, the Poincaré group, I need. So I still want a quantum space-time. But what happens, and this is the central point of the second half of the seminar, is that not only I require quantum space-time, but if I have a quantum space-time, I will require quantum symmetries. So not only I have to change the structure of space-time, but I have also to change the structure of the transformations of space-time. The simple things like translation, rotations, and boosts. And these quantum symmetries were introduced with the formula of quantum groups and of algebras, and they are actually developed in parallel to non-commutative geometry. And there are lots of connections between the two, but they are technical, and the names that we developed that are Voronovitz, Drinfeld, Lukierski, and other people. So I will take a particular deformation of the Poincaré algebra of the symmetries. Again, I can deform symmetries in a variety of ways, and it's interesting to deform the Poincaré, and I will consider the symmetries which are a deformation of the symmetries. So Poincaré group is rotation, boosts, and translations. And there is a mathematical formalism that makes this. And the space which emerges from this deformation. Now, this deformation, for technical reason, was done as to do with the sitter. Anyways, I take this because because I take this. I could take other things, but it would take me a seminar to justify. And so I have another different set of commutation rules. Now, before I had the space coordinates were not commuting. Here I take space coordinates which commute. And I take the time coordinate which doesn't commute with the 3 space coordinates with this formula. So you see, this is not a constant anymore. So this is a more complicated thing, of course. This lambda is the deformation parameter which, for quantum mechanics, which is again can be seen as a deformation. In fact, there is deformation quantization, which is so this parameter lambda is the deformation parameter analogous to h bar, and the space is called Kapp-Minkoski because the original papers, what I call lambda, they were written in terms of 1 over kappa. Kappa is like the analogous of the speed of light. So people were coming from relativity. So historically, they thought of a big quantity. And but I'm from quantum mechanics, so I prefer to have small quantities. So the quantity that goes to 0 rather than infinity. The formulae are simpler. So So I call it Kapp-Minkoski, that the parameter is lambda. It is 1 over kappa. So it's an historical, and I will consider only kinematics and leave alone H bar for the moment. So I will I will not discuss the fully quantum space. So it's only, I'm only quantizing classical relativity in this sense. I'm studying this non-commutative space in this sense. But I will worry about Poincaré transformation. Now, this is the first red one. And quickly, what I did when I do quantum mechanics, I have that in the Schrödinger representation, position is a multiplicative operator and momentum is a derivative. Now I have that I can say that position is a multiplicative operator and time is an operator, and is basically a dilation operator. So the 3 halves is because I want this to be symmetric, asymmetric operators. In 3 + 1 dimensions will be 3 halves, otherwise will be the number of dimensions. And so I do this, and things become simpler in polar coordinates. And these are the commutations in polar coordinates. The angular variables don't commute, and only the radial coordinate is the one that doesn't compute. The hat is missing here. But this one, I cannot do different backgrounds within the same slide. This is an important formula, because this is the generalization of the Heisenberg principle. And you see that the generalization is not, there are 2 operators we don't commute. The 2 operators are the radial coordinate and time, but their commutator, their uncertainty, the combined uncertainty, must be larger than the most probable, the expectation value, the average value of the distance. So it's not a constant here. So it's something which grows with distance. So this is something which grows with distance, and I have to worry about it? Because of course it's something which becomes larger, and then I had already thought of this, but Nick and Tushar asked me. So this means that the farthest I am, the more uncertain I am, which is also true for usual Heisenberg principle. So I know that I cannot know precise position and precise momentum, but yet I know that I'm here and I am at rest. And the fact that I know with high precision that I'm here doesn't mean that you don't know where I'm going. And because H bar is small. Now, this lambda, I'll take it to be the Planck length. And so the most precise click experimentally is 10 to the minus 19 seconds in some experiment. I looked at it on Wikipedia. So this is my uncertainty. Now I use x0, which is t times z, times c times t. And so this would be t. And I say that, so if this is the quickest click, the uncertainty will be probably less than that, but at least that. So delta x on 0 in meters is 10 to the minus 11 meters. Most precise distance that has been measured is at the Large Hadron Collider, which is not something that is very portable, but this is the smallest distance in which we know that physics, as we know, quantum field theory, works well. We don't have to put quantum gravity. So is this. So again, I assume that this is the uncertainty, the maximum uncertainty. And so if delta x here, that's R, is 10 to the minus 29 square meters. If lambda is 10 to the minus 35, I have to start worrying when R is 10 to the 6 meters. So when I am at the distance of 1,000 kilometers, then then I have to worry that there is an uncertainty that I can detect with the fastest clock that I have and the LHC. See, now I didn't write it, but I thought I did. This means that if instead the distance is the difference between Earth and Moon or something, then you get to millimeters. That's some sub-micron, so very, very small distances. So now so I don't have, like for Heisenberg, I don't have to worry about. There are even grains of dust. The Heisenberg principle doesn't work. It works for electrons, of course. It's very important for electrons. So I say that the spectrum is the possible result of a measure. There is an S too much. It's incredible. You read it again and then live you will find lots of typos. So this could have been read. So what are the possible results of a measurement of time? And fortunately, time is, I can measure time from -infinity to infinity. This is not, I'm playing with operators. I've written everything in terms of operators. So I have to look at the spectrum. Technically, I have to make sure that the operator is self-adjoint. There are a variety of things, but the spectrum is okay. Time goes from -infinity to infinity, and R, which is the spectrum of the distance, goes from 0 to infinity. So, in quantum mechanics, the change between Q and P are connected by a Fourier transform. And in Kapp-Minkoski, I have a Mellin transform. Now, a Mellin transform is something that I can write with the log exponential of a log, or this is a monomial. So it's like the Fourier transform. Fourier transform is you take a function and you make it as a sum of sines and cosines. And instead you take a function of cosines of logs. So it's there are some constants here because I'm in 3 dimensions and something. So, but everything is under control now. The physics seminar, this slide was a good chunk of the seminar. And now I have that I cannot measure time and position at the same time in the radial distance. Is there a duality that I like the one that I have in quantum mechanics? So if I have a Gaussian measurement of position, which is very sharp, then the Gaussian in the momentum is very wide. So yes, there is, except that doing it Gaussians is not simple. So what we do is we localize some state in some portion of space. This is a cone of an angle, and this is a little pill there. And I can make this to become as small as I want. So I can localize. The reason for this is that this way I can do the integrals. I don't have Gaussian integrals, so I can do the integrals in this state. So if I localize, if I send A to 0, the angle also closes by. So I'm localizing in the distance. And here. Now I do the Mellin transform, and again, I can see that, and actually today I discovered that there's some constant missing here. It's the same. If in a concrete example, if I localize in space, I delocalize in time. If I delocalize in time, I can, in space, the two of them work this way, but it's important also the distance. Now, however, if I am far away, I have this delocalization, but let me remind you, if R is near 0, then it's exactly 0. So near the origin, then I can localize states very much. So I can not localized states which are far away. Now I do far away, but I know that I should be far away at distances. But so the question that I ask, that is natural to ask, is that is the origin a special point? So what is going on? So I'm after all Einstein, etc. So I have the origin of the universe. Everything works here. So now I have an observer, or alias reference frame, because I'm putting everything in in a reference frame. Now, this we were discussing this today morning. People coming from relativity like to think of reference frames, set of coordinates, etc. If you come from quantum mechanics, it's more natural to think of an observer. So a set of operators in a reference frame, but this is an observer, and then I can change with a unitary transformation and make into a different one. So they are not the same thing, but for the purpose of this talk, whenever you see observer, you can think of. So there isn't, of course, a kappa origin where the kappa god is sitting and everything is measured away from him, because I have chosen a reference frame, and I've chosen this reference frame, this observer located with an origin, and for him, here and now makes sense. This is not non-trivial. So he can localize where he is, at least, and where things near him are. And okay, I solved the problem of the pronouns by alternating he or she. So being not a native English speaker, I can make mistakes, and I found this it was a mistake I was making at the beginning. So I alternate here. Him and her is the same person, but is transgendering in the same sentence. So this observer cannot localize away from him, but he can localize where he is. Then what happens when there are other observers, other reference frames? So this other observer will be translated, rotated, and boosted. We'll see that translations are the problem. And he will have his own states, etc. Now, usually we are thinking of these operations done the classical way. So I take quantum mechanics, a unitary operator that involves translation, commute, and everything is under control. But now, as I said, I need to have a quantum symmetry. So in order to move, I need to implement these transformations with a quantum group. And a quantum group is something where things don't commute anymore, not necessarily commute. There are various aspects. I concentrate on one of them. And so quantum groups have two aspects. One, which is the one that I will treat here mostly, is that the parameters of a transformation, so if I translate by a certain amount, in general, not only the translations commute, but the parameters of the translations commute because they are numbers. Even a rotation is a matrix, 3 by 3 matrix. The entries of the matrix are numbers. So the matrix don't commute with each other, but the elements of the matrix are numbers. Here, the elements of the matrix are not number anymore, or the elements of the translations need not be numbers anymore. So I am in a further level of, so the quantum groups have non-commutativity, but it's not that the group is non-commutative. We know rotations are not commutative, but the elements of the groups are non-commutative. Okay? And this also means that there is non-co-commutativity, where if I put together representations, so if I act on two states, the way in which I put together the action on two states, for example, infinitesimally, the action of the derivative on the product of two functions has to be done with the with the Leibniz product. It's not the derivative of one times the derivative of the other one. I know how to put them together. In this case, things are complicated. Okay, so I have this kappa Poincaré, and I want to concentrate only of this. There are various representations, and let me concentrate really on this. This is the translations, and mu and u go from 0 to 4. Basically, this is the A0 AI equals to lambda AI. So this reproduces the non-commutativity of the coordinates. It's not the case. It's because space-time is the homogeneous space, but the elements for the rotations commute. That doesn't mean the rotations commute, but the elements of the matrix. And I put them together, then I get a rather complicated objects. But this is probably the most interesting thing, the most important thing. So translations are non-commutative. So if I translate, I have to translate in a quantum way. So what did I do? I started with a space, and I started to describe it as I do with quantum mechanics, with operators. But now I have to describe also the symmetries as operators. The symmetries, the reference frames, the observers are operators. So if I was describing positions with wave functions, now also symmetries, translation, will have to be described with wave functions. So I have an Hilbert space which contains both space-time and the symmetries for space-time, if I want to make this transformation. In reality, this is always done. In fact, measurement, I take the Wigner friends and everything. So the paradox is that it's a quantum object, but this Hilbert space is trivial. It becomes classical because everything is decohered, etc. But here I have to do the same, and I do it with the formally for quantum group algebra. And so now the Hilbert space will be functions of either R or time. Tau is the a-dimensional versions of time. But now, so I have functions of R, say, and functions of A, and functions of the lambdas. And okay, in this particular case, non-commutativity is present in the translation sector. There are various flavors, but in this case, translations is the important one. This means that I have to translate with this non-commutative space. But this means that if I have a different translated observer reference frame, I have an uncertainty in the translation. So I know that there is another observer. So I translate, I change the observation, but seen from the original, in the original observer frame, it's impossible to localize where the other observer is. And okay, before I go there, I have a nice classical metaphor for this. Suppose that those that are following me remotely, and suppose that they don't know Oxford and the philosophy department very well. So they roughly know where I am. I know that I'm in Oxford, in somewhere. And so they have a not very sharp localization of where I am. But they know that this pen is near me. So if I tell them that I'm sure that this pen is 5 centimeters from me, they know where the pen is, except that they don't, because they don't know where I am. So they know that the pen is near me, but I am somewhere in Oxford. Of course, classically, I give them the GPS coordinates of my nose and the GPS coordinates of this, and because I can make it sharper and sharper. In this other case, different reference frames, of course, we say that it's not really somebody sitting here and somebody, there is no Schrödinger-Cat paradox really at work here, but it's clear that the other reference frame has some sharp origin, unique for that reference frame, except that I don't know very well where this reference frame is. And that is solves the paradox pretty much. Okay, here there are some technical things. Again, I can, so in 1 + 1 dimension, everything is under control, although 1 + 1 dimensional is a bit pathological because the Lorentz group becomes only 1 parameter boosts along the only direction. So, but we can do everything. So I enlarge the phase space and I have everything under control. The boosts are depending on one rapidity variable. So there is only 1 parameter. So there are three parameters, A0 and 1, and Xi, which is the boosts, and this is the commutation rules. And you notice that when Xi is 0, so if I don't boost, then this goes to 0, which is okay. So if I can at least localize myself, which is not true for Heisenberg. Heisenberg in phase space, I cannot localize myself. And this is the action on the phase space. And I can create states, and I know how to transform positions in this under control way. And so if this is the state of the transformation, the expectation value of the position is translated by the expectation value of the translation. And so the expectation value of coordinates is exactly, so this is a transformation of the origin, and the transformation of the origin depends only on the wave functions of the translation and other things. So monomials, I am slightly running out of time. So this is, monomials are okay. And one interesting thing is that if I translate, I increase uncertainty. So if I don't know something with some uncertainty, if I translate, the uncertainty grows because of this. Okay, this is what I said before. Now let me mention 2 things to finish. There is something which is called the relative locality, which is a work by Amerino, Camelia, Kowalski, Glickman, Fedele, and Smolin. And they are compatible with us, but there is not a one-to-one translation. For them, the important bit is that momentum space is curved. This has to do, momentum space is the generator of translations. So you have a space with the curved momentum space, and there are kappa Poincaré there, everything. And so the two views are similar. Okay, this, well, I was thinking whether to say this, it's while I think of saying, this is very small, so this may be unobservable. However, there can be amplifying effect on cosmological scales. So there can be phenomenology of this kind. There are several people working on the phenomenology of quantum gravity in this sense. So even if h bar and the Planck length are small, or even if h bar is small, certainly its effect on macroscopic objects is not zero. It's because there are amplifying effects because the atoms they put together. So there are people trying to understand this. Now I want to mention something which is a dual approach, and then I'll finish. Because quantum observers appeared recently in the literature, also in the work of Flaminia, Giacomini, Bruckner, Castro-Ruiz. If you have quantum observers, then you have one important characteristic of quantum mechanics, of quantum physics, which is entanglement. So they got there from the quantum information angle. So they started to think of observers which are entangled, which are in an entangled state, or they call them quantum reference frames. So reference frames, which are two reference frames, which are in an entangled space. And then what is interesting, and by starting with this entangled space, and entangled reference frames, the transformation between reference frames become quantum, and localizability becomes a frame-dependent concept. Therefore, starting from the imposition that reference frames are quantum, they get to quantum spacetime. So it's the other way around. I started from quantum spacetime because I do noncommutative geometry. So I started with a noncommutative geometry, and I was forced upon saying that observers and reference frames are quantum. They started from reference frames. They do quantum information. Reference frame is a bit of information as well. And they found that localizability of the events that this reference are putting together gets lack of localization. So they don't have the black holes that I said at the beginning, but they reach exactly the same conclusion from the other way around. So they don't have Kapp-Minkoski or anything. So this is the end. And so we have enough problem with classical observer dealing with quantum cats. Now we have quantum observers dealing with quantum cats and Wigner quantum friends and so on and so forth. And that's it. Thank you.
We'll take 5 minutes, I guess. Yeah.
I am impressed. I finished 3 minutes late. That clock is if the clock.
About 5 minutes later, so I think you're actually under time.
Okay, that's that's fine.
I just
No.
Still.
Okay.